So this is part one of numerical methods for partial differential equations practice final exam. So let's begin. Number one, consider u sub t equals kappa u sub xx, where 0 is less than x is less than 1, t is less than 0 with homogeneous Dirichlet, boundary conditions, and smooth initial data. Some say in anglicized version Dirichlet, but we'll say Dirichlet. I'm sorry, I'm not good with pronunciation. Um, so, so Dirichlet, boundary conditions, and smooth initial data. Use the explicit finite difference method. Use u sub j superscript n plus 1 minus u sub j superscript n over delta t equals kappa times the quantity u sub j plus 1 superscript n minus 2 u sub j superscript n plus u sub j minus 1 n. We'll just call it n instead of saying superscript for brevity for the rest of the problems, over delta x squared. So parts A, B, C, D, and E, derive the local truncation error, perform the von Neumann stability analysis, find the sharp stability condition on R equals kappa delta t over delta x squared. Part D, explain why consistency plus stability implies convergence. And Part E, estimate the global order of accuracy. So this is a consistency, stability, convergence for the heat equation problem. So we write out our scheme: u sub j superscript n plus 1 equals u sub j n plus r quantity u sub j plus 1 to the n minus 2 u sub j to the n plus u sub j minus 1 to the n, where r equals kappa times delta t over delta x squared. For our Taylor expansion, u sub t equals u sub j to the n plus 1 minus u sub j to the n over delta t minus delta t over 2 u sub tt plus there the order delta t. So u sub xx equals u sub j plus 1 n minus 2 sub j to the n plus u sub j minus 1 to the n over delta x squared minus delta x squared over 12 times u sub xxxx plus order delta x to the fourth. So our local truncation error is tau equals order delta t plus order delta x squared. Okay, so building on that, see if this all, whoops, change this. Sorry. So for this, for the von Neumann stability, what we do is we insert u sub j to the n equals g to the n e to the I j theta. Then our g equals 1 plus r times the quantity e to the I theta minus 2 plus e to the negative I theta. And that equals 1 minus 4r sine squared theta over 2. And stability is going to require that absolute value of j be less than or equal to 1. So since g is real, negative 1 is less than or equal to 1 minus 4r sine squared of theta over 2, and that's less than or equal to 1. And that gives us that, and then from there, the sharp condition is 0 is less than or equal to r is less than or equal to 1/2. And by the Lax equivalence principle for linear well-posed problems, consistency plus stability implies convergence. So the norm here of u to the n, capital U to the n minus lowercase u to the n, that equals order here for delta t plus delta x squared. Okay, so that's number 1. Moving along now to number 2. So for the same heat equation, consider the backward Euler. Sorry about that, backward Euler. So we're going to get the following. For u sub j n plus 1 minus u sub j n over delta t equals kappa u sub j plus 1 n plus 1 minus 2 u sub j n plus 1 plus u j sub u sub j minus 1 to the n plus 1 over delta x squared. So that's what we're given here. Part A, write the method in matrix form A, u to the n plus 1 equals u to the n. Part B, describe the matrix A. Part C, prove that A is non-singular. Part D, prove non-conditional stability using either eigenvalues or an energy method. In Part D, compare the computational cost of solving each times step by dense Gaussian elimination, tridiagonal direct solve, Jacobi iteration, and Gauss-Seidel iteration. Okay, so this is an implicit time and stepping matrix structure problem here. So the scheme is here u sub j n plus 1 minus r times the quantity u sub j plus 1 n plus 1 minus 2 u sub j n plus 1 plus u sub j minus 1 n plus 1, and that is equal to u sub j n. Now equivalently, negative r u sub j minus 1 n plus 1 plus quantity 1 plus 2r u sub j n plus 1 minus r u sub j plus 1 n plus 1 equals u sub j to the n. So a u to the n plus 1 equals u to the n, where we have the following with this matrix. This a equals this matrix given here. Here are the entries, rows, and here are the columns. So the matrix is tridiagonal, symmetric, strictly diagonal dominant, and positive definite. Now moving along for any vector here for this, that we're going to get the following, right? So we get the following for any vector. V cannot be equal to 0, so A is non-singular. And for stability, the eigenvalues of the discrete Laplacian are non-positive. If lambda is less than or equal to 0, then the backward Euler gives the following amplification here. G equals 1 over 1 minus delta t kappa lambda. And since in that denominator 1 minus delta t kappa lambda is greater than or equal to 1, the absolute value of G has to be less than or equal to 1. So the method is unconditionally stable. So our costs here for dense solve, order n cubed, try diagonal solve, order n, Jacobi Gauss-Seidel, order n per iteration. And Gauss-Seidel usually converges faster than Jacobi. However, both can be slow for fine grids. All right, so that's number 2. Moving along now to number 3. Consider Crank-Nicholson applied to the heat equation here. Here's what we're given. U to the u sub j n plus 1 minus u sub j n over delta t equals kappa over 2 times the quantity u sub j plus 1 n plus 1 minus 2 u sub j n plus 1 plus u sub j minus 1, the n plus 1 over delta x squared, plus u sub j plus 1 to the n minus 2 u sub j to the n plus u sub j minus 1 to the n over delta x squared, close bracket. So here are the 5 components. Derive part A, derive the amplification factor. Part B, show that the method is unconditionally stable. Part C, determine its order of accuracy. Part D, explain why Crank-Nicholson may produce non-physical oscillations for non-smooth initial data, even though it is stable. And Part E, propose one practical remedy. So we have a Crank-Nicholson and oscillatory error problem. We'll let u sub j to the superscript n equal g to the n e to the ij theta. The centered second difference contributes negative 4 sine squared of theta over 2. So we get g minus 1 over delta t equals kappa over 2 delta x squared, quantity negative 4 sine squared theta over 2 times that g plus 1. We're going to let mu equal 2r sine squared of theta over 2. So g is going to equal 1 minus mu over 1 plus mu. And mu is greater than or equal to 0. And absolute value of g is less than or equal to 1. So the Crank-Nicholson is stable. Our local truncation error is order delta t squared plus delta x squared. So the global accuracy is order delta t squared plus delta x squared. However, if mu is much larger than 1, then g is approximately -1. So high frequency modes are not strongly damped. They may oscillate in sign. This can cause non-physical oscillations for non-smooth initial data. A common remedy is a Renneker smoothing. Take a few backward Euler steps first, then switch to Crank-Nicholson. Okay, so that is part 1. Thank you very much and have a great day.